Okay, so here, this is the 30 plus why the bearing A was going to be the one at the side here. And this one actually not going to have any radial load. All the load is going to be handled by this radial bearing. Okay, and the shaft is rotated at 200 RPM and is going to be used in piece of the agricultural equipment. We need to specify the suitable tapered rollers bearings for the shaft. So the Z we said is going to be 0 here, and you're going to do your calculation. But for me, I'm going to have the example that I got from the textbook, and we're going to go through it. By the way, the process is not too complicated for any example, because you can see I can put them in an Excel sheet, and that's what's happened to that question. And by changing the parameters, for example, for your Q or the Z or the PQ, I can find all the loads first, calculate for the FRA, FRB, and the TA, and we're going to assume a certain value for the YA and the YB. Do calculation for all, find the C value, select the bearings from the table, and we're going to add the parameters for the bearing here, and I'm going to find the final results for the PA and the PB. So it's not that hard. If I can do it with the Excel sheet, you can do it also on an Excel sheet. And for the previous question also, I did on an Excel sheet, and this can do multiple iterations. One of the things that you need to change manually is going to be, for example, the value for the E's. So it's going to do the interrelation to find the value for the E and the value for the Y. Now we have this case, we have thrust load and we have radial load, and let's try to do the calculation for this type of the bearings. So in the case of the tapered roller bearings, we're going to have the PA and the PB going to be quite different, because the PA is going to be the one that's going to take both the radial and the uh, uh, normal forces, while the other side is going to be only the normal forces to be applied, or the reaction force, if you can call it. So here we have the PA is going to be equivalent radial loads on the bearing A, the PB is equivalent radial load on the bearing B, the FRA is going to be applied radial load on the bearing A, the FRB is going to be the applied radial load on the bearing B, TA is thrust load on the bearing A, YA is thrust vector for the bearings A from the tables, and the YB is going to be thrust vector for the bearing B from the tables. So when we say tables, this is table 14.7, and it's going to be about table roll and bearings type. So it's depends once again on the diameter of the board, the outside diameter, the width, the A value, and the thrust factor Y, and the basic dynamic load C. Remember that the dimensions here are going to be in inches, the load C is going to be in pounds for the L10 life of 1 million revolution. So the example we have here, which is similar to the question that you have, is going to be a shaft shown in the figure 1415 carries a transverse load of 30,246 Newton, okay, which is 6,800 pounds, and thrust load of 11,120 Newton, and the thrust is going to be resisted by the bearing A. The shaft rotates at 36.64 radian per second, which is equal to 350 RPM, and is to be used in a piece of agricultural equipment. So tell me now the application, the RPM value, and of course I can find the life and I can calculate the value for the C, and then from the C, for both bearings, I can calculate what will be the value for the what will be the best bearing we can have from the table 14.7. So the solution is start with the radial load in the bearings can be calculated as the following. The FRA is going to be three, sorry, 3,246 this value multiplied by the 101 multiplied by 6 divided by 254 millimeters. So what we've done here is I know this load on the gear, and I would like to find what will be the radial force here. So simply, again, to fix the shaft here and do the moment equation. Okay, do the moment equation. So the FRA, direction at the bearing A, is going to be equal to the radial force multiplied by the distance from the C to A and divided by the total distance. And then I'm going to do it on the other side, or I can do the sigma of the forces to the y direction is going to be equal to 0. Then I can find the FRB as well. The TA is given as the 11,120 Newton. Now, assume the value for the YA and the YB to be 1.75 each. And then I'm going to apply it to the equation 14.8. So by applying this equation, I will find out that the value for the PA is going to be equal to 33,373 Newton. So now we calculate the PB, which is going to be equal to the FRB, which is 18,147 Newton. Now select the 4,000 hours as a design life, and the LD in that case is going to be equal to 4,000 multiplied by 350 RPM multiplied by 60, and this will be 8.4 multiplied by 10 up to power 7 revolution. Now we can calculate the C by using the equation 14.3. So we can calculate the C for both bearings because we have the PA, we have the life for design life, okay, and we can apply the equation directly. So the CA is going to be the PA multiplied by the life, which is going to be the same, divided by 10 up to power 6 up to power 1 over 3.33. This is a taper shaped roller bearings. For the B, I'm going to change the PB instead of the PA. Now, 33,373 multiplied by 8.4, 10 up to power 7 divided by 10 up to power 6, up to the power 1 over 3333. Sorry, this is typo. I'm going to change it soon. Just give me 1 second. Okay, let me change that now. Okay, that's 3.333. That's 1.333. Because I'm going to make another video later for the question that you're already going to do in the class. Okay, save that. Okay, so yeah, we're calculating the new C value. The C value is correct, I know that, but I just forgot to put that. So we're going to have the CA is going to be 124,323 Newton, and for the CB it's going to be 68,499 Newton. And now I have these values. I can go to the table 14.7 to find my bearings. So now I calculated the C value. The one I calculated was in Newton. I need to have that in pounds. So again, to multiply it by the factor to convert it to a pounds. So the 124,323 Newton is equal to 27,948.9 pounds force. And for the CB is going to be 15,399.2 pounds force. So I locate for the C value. For the CA, 124, which is 27,984. So I will look on the table here. I have here 26,000, no, 29,300 is okay. So this will be the bearing A. Bearing A is going to have a diameter of the 2.5 inches, the outside diameter of 5 inches, and the C value is 29,300, and the YA is 1.65. Remember that I found here the YA. The bearing B now is going to be based on the value of 15,400. So I have here 12,000, that's 21,000. So I'll choose the 25,000 as the candidate. And this will tell me the diameter of the bore is going to be 1.75. The outside diameter is 4. The width is 1.25. The A is 0.97. And the Y factor is 1.5. Now I got these two bearings and I will check what will be the value for the P now, based on the new YA that we found, or the value of the C actually even can be found. So we will compute the equivalent loads, the PA and the PB. Okay, so you can see that this value has been actually dropped because the value for the YA has been dropped. Okay, so no, actually it has been increased. Yep, because this ratio has been increased. So we found the new values for the PA and the PB, and one caution must be observed in using the equations for the equivalent loads for the table roller bearings. If from the equation 1418, the equivalent load on the bearing A is going to be less than the applied radial load, then the following equation should be used. If the PA is going to be less than the RA, then let the PA is going to be equal to the FRA and the compute for the PB. So again, to reverse the equation to be that way, okay, and the other equation is going to be also changed. Okay, so that's it. That's how to solve for the table equations. And again, to provide you with a solution for the question 4 and 5 based on the parameters we have on the example sheet.